a coherent sweet plane slicer for layered manufacturing. This is a paper. It's kind of an old paper, 1999, but I just went through the grapevine research to find kind of an older, more rudimentary description of how slicers were working. And this had some good background, so this is the paper I decided to delve into. Yeah, so just a quick introduction, right? What I want to go over is just the basic slicer principle that was explored in this paper, at least, and just talk a little bit about the data structure that was used by the algorithm, and look at some of the steps that the algorithm has to go through in order to work well. I'm not really going to go super in depth in the algorithm, but just kind of introduce some of the things that they're looking for, how these points are identified, and how different things are determined. That's more of a computer science topic, and that's certainly not my area of expertise. Yes, so my cursor out of the way there, perfect. What happens in a slicer is typically, I mean, nowadays you can use things other than just STLs, at least I think. Anyways, wait, I know for a fact you can. But anyways, generally, right, something like an STL model describes the geometry of your part. And then what happens in a slicer is it goes through and it identifies, bring the cursor back, layer to layer to layer, where to deposit material, right? So what it's really doing is you get your part and then you get these two-dimensional contours, and then the last step is figuring out the path to fill in these contours, almost like a coloring book, right? Page, 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 coloring them in. And that tool path, or how to fill those in, that turns into G-code. So I want to just define some things, right? So a vertex, like this point right here, is a point, right, that can exist in, well, it can really exist in n dimensions, but we're going to say it exists in 3 dimensions, where 2 edges meet. What are edges? Well, it's a line segment between 2 vertices. A face is a plane bound by multiple edges. So we have vertex, edge, and then here, this whole thing is a face. And then another thing that can be kind of important, and you might see this in Slicer sometimes, is non-manifold geometry. And so in this paper specifically, the thing that they were concerned with is when an edge is shared by more than 2 faces, but there are actually lots of other examples of non-manifold geometry. So like if this cube had just a single face coming off of it, but it wasn't like bound anywhere, so it was like not physically possible to have an infinitely thin slice of matter, that would be non-manifold. Yeah, so an STL is definitely not the best organization for slicing algorithms. It is really nice and generic. That's why it's used, because it is so generic. But if you really want to start performing algorithms on things like STLs, you need to take the data and you need to parse it and essentially reorganize it. And so the authors of this paper created their own data structure to describe a face by its edges, and then the edge, no surprise, is described by vertices, and things that are all linked together, they're kind of referenced together. So that allows this data structure to be easily indexed from one edge to the next connected edge, and so on and so forth. And so having this well thought out structure can be really useful. But you can see right here, right, the most basic thing that our geometry is constructed out of is vertexes, or vertices, sorry. And so right there you've got your X, Y, and Z components there. And those are building blocks that build up edges, and then edges build up faces. And you can see like a face is just a list of edges that are used. The sweep plane algorithm is probably your most intuitive idea of what a slicer might do, right? And so that concept is that a virtual plane goes step by step through your model and observes, right, which edges intersect with said virtual plane, right? As that plane goes up, you see what intersects with it. And you keep track of the vertices that do. So you can see here at this particular slice, F, K, J, I, H, and G, right? These edges, that's what these letters are representing, the edges. They all link together there. And then in the interior here, we got A, B, C, D, and E. They're also linked together. And we see that they are right intersecting that plane. Something that they make special note of in the paper is identifying pseudo-2-manifold edges. This is something that could break up, kind of break apart their algorithm, and that was when you have an edge that is shared by two distinct pieces of geometry like this. So it's something that they would have to detect and specially care for. One of the biggest things that they needed to do in order for their ideas to work out properly was identify what type each vertex was. And so the types that it could be it could be beginning, ending, mixed, or saddle vertex. And so let's look at what each one of those looks like. A beginning vertex, hence the name, is a vertex, like this guy right here, that indicates that. And remember, our slicers typically go from the bottom up, so they're starting at the bottom of the screen up to the top. And so when we get to a beginning vertex, that means new contours will be generated by the sweep as it goes up. So once we go past this vertex, that means new geometry is going to be generated. No surprise we have the opposite way, right? We have the ending vertex. And so the ending vertex is when, just a second, let me stop my little notifications. And as we head up here, when we hit this specific ending vertex, that means that no more contour is going to occur, or no more geometry is going to occur after this vertex. I mean, there are some special cases when it might, but if it's unless it's identified specifically as an ending vertex. There are also mixed vertices, that basically indicate that the size or the shape, rather, of the contour is going to change after this vertex, but there's still going to be contours that are generated above a mixed vertex, right? And then kind of our really special one is a saddle vertex, where you can imagine as we slice this object, we'd have kind of a bigger shape, until we get to the saddle vertex. Once we go above that, we're going to start generating separate contours after it. So it's almost can kind of be treated as a beginning vertex, but it's not quite the same as a beginning vertex. So using all of that can really inform how the slicer operates when it goes through and what types of contours it generates and when to generate contours. This is all work that helps the algorithm work much more efficiently, where it's actually required by the algorithm the way they wrote it. But another thing worth noting real quick is once the contours have been generated, an important thing would be to identify what is the exterior and the interior contours. If you have a solid thing like a cube, that's fine. But in this case, we have like a cube with a hole in it, right? We know that this is exterior, right, this area. And then once we intersect this first edge, this has to be interior. And then we intersect another edge, this closed loop, right, this closed loop contour. Once we intersect this edge, then we know that this is exterior. Then we intersect this edge and it's interior. So that's something that's supposed to be that has to be specially cared for, because obviously we want this to be empty area, and so that's something that's identified by the algorithm. Something that was utilized in this algorithm was the idea of coherence, and identifying, right, once you identify what type of vertices you have, it can save calculation time later in the algorithm. For example, if you consider this shape, if we know that this is a start, and we know this is a starting vertex, and we know that there's not going to be any other vertices for a while in here because we've classified everything properly, this no longer becomes really algorithm and searching, and rather what it becomes is just geometry, because we know there's no vertices from here to here essentially. And so what that means is this can all be solved geometrically, right? We know that if we go up a certain increment, that these straight lines, right, with their slopes, we can determine where the points would where the lines would intersect with that plane, and we can just go up. And so using that information and knowing this is a starting vertex and knowing where our ending vertices are going to be allows us to not have to search through our data anymore, and instead just go through and calculate what those contours are going to be. So what's next after we've generated all of our contours? Because that's what's really is happening in the slicing algorithm, is we are getting our contours. So once we get this big stack of contours, what we can do is, or what we need to do is start filling in those shapes, right? Filling out those paths. And so what that's going to be is basically iteratively deflating polygons, or figuring out the polygon that fits perfectly inside that polygon, and then one that fits inside of it for things like walls and surfaces. Otherwise, you might be doing something like finding the intersection of a grid or whatever your infill pattern is with that contour that you've generated. And so that's something that we'll look into later.